Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and this is lecture number 24 on chemical kinetics. In this lecture I will explain Arrhenius equation which he has given for the chemical kinetics, and it is a relation between rate constant, energy of activation and temperature. Mainly there are many factors which affect the rate of reaction. Okay. There are so many factors which affect the rate of reactions. And one of the important factor is temperature. Temperature of the system. It's very simple that on increasing temperature, rate of reaction increases because energy is given to the system, and therefore when energy is given the rate will be always high, but it is of forward reaction as well as reverse reaction, or according to chemical equilibrium, on increasing temperature the rate of endothermic reaction increases. To be very precise, we can write like this, that rate of endothermic reaction increases. Why? Because in endothermic reaction energy required, so when energy is given, definitely rate of endothermic reaction increases. And on the other way, if you on decreasing temperature, the rate of exothermic reaction increases. Okay. But for any chemical reaction, first of all, energy is required, and that is why there is exponential effect of temperature on rate of reaction, and that is given by Arrhenius, and that is called Arrhenius equation. So Arrhenius equation is the relation between rate constant and energy of activation and temperature. So K proportional to e raised to minus EA upon RT, where R is a constant. If you want to put equal sign, we need one more constant. See, K is rate constant, so we can't use K over here. So that is not proportionality constant. So we use another constant, and Arrhenius kept A for him. So A into e raised to minus EA upon RT, where A is known as Arrhenius constant, Arrhenius factor, Arrhenius constant, Arrhenius parameter, or it is also known as proportionality constant. Okay, so now if we want to simplify this, we can take log on both the sides. So 2.303 log K is equal to 2.303 log A minus EA upon RT. If you simplify more, then it is log K is equal to log A minus EA upon 2.303 RT. Okay, this is known as Arrhenius equation. Okay, where EA is energy of activation and A is Arrhenius constant. Okay, and we can plot a graph, okay, like this one. Here, with reference to this, we write log K versus 1 upon T. So it will be a straight line, and slope, that is tan theta, is equal to minus EA upon 2.303 R. So from this we can find out EA, energy of activation, if you know R. Okay, so this is the way we can use Arrhenius equation to find out energy of activation. Or the another method is, if you do not plot a graph, then we have to carry any chemical reaction in two different conditions. Okay, Like suppose at T1 temperature, the rate constant is K1, and at T2 temperature, the rate constant is K2. Then, according to Arrhenius equation, we can write log K1 is equal to log A minus EA upon 2.303 RT1, and log K2 is equal to log A minus EA upon 2.303 RT2. Okay, so we take difference of these two equations. So log K2 minus log K1 is equal to log A minus log A cancelled. So minus EA upon 2.303 RT2 minus EA upon 2.303 RT1. A upon 2.303 R will be common. So log K2 upon K1 is equal to, minus sign is also common, so minus EA upon 2.303 R bracket 1 upon T2 minus 1 upon T1. Okay, or log K2 upon K1 is equal to minus EA upon 2.303 R bracket T1 minus T2 upon T1 T2. If you want to put negative sign inside, then we can write log K2 upon K1 is equal to EA upon 2.303 R bracket T2 minus T1 upon T1 T2. So this formula is also, or this equation is also used to find out energy of activation in different cases. Let us take one example so you come to know. The gas phase reaction between methane and sulfur is given, like CH4 gas plus S2 gas gives CS2 gas plus H2S. This reaction is used to prepare CS2 carbon disulfide. Okay. Now, this is given at 550 degrees Celsius. The rate constant for this reaction is 1.1 liter per mole per second, and at 625 degrees Celsius the rate constant is 6.4 liter mole inverse second inverse. So you have to calculate energy of activation. Okay. So what is given? From this data we can say that K1 is given. K1 is 1.1 liter mole inverse second inverse. So T1 would be 550 degrees Celsius. So you should convert this Celsius into Kelvin. So it is plus 273, so that is 823 Kelvin. K2 is 6.4 liter mole inverse second inverse. For that, T2 is 625 degrees Celsius, which is equal to plus 273 will be 898 Kelvin. Okay. Now we can use formula of Arrhenius equation. Log K2 upon K1 is equal to energy of activation upon 2.303 R bracket T2 minus T1 upon T1 T2. Substitute values of all. So log 6.4 upon 1.1 is equal to EA, which we want to find out, 2.303. If you put 8.314 as R, then your answer will be Joule. That is 898 minus 823 upon 823 multiplied by 898, and here answer will be in Joule. If you take R equals to 2 calorie, then the answer will be, and then energy of activation will be in calorie. Okay, so this way you can calculate energy of activation and the unit will be joule per mole. Okay, thank you so much.